physicsacademy.co.uk presents the Standard Model of Particle Physics. The Standard Model of Particle Physics attempts to categorise all the known subatomic particles into groups in the same way that the periodic table categorises atoms. The first group of particles are the fermions, from which all matter is built. The second group are the bosons. The bosons are the force carriers, and it is the interactions between fermions and these bosons which holds all matter together. The main difference between fermions and bosons is their spin values. Fermions have half-integer spin, and bosons have integer spin. Particles with half-integer spin cannot exist in the same space at the same time in accordance with the Pauli exclusion principle, and are described by Fermi-Dirac statistics, whilst integer spin particles can exist in the same place simultaneously, with their spin states described by Bose-Einstein statistics. Fermions are grouped into three vertical categories, which are known as the three families of matter. The fermions are also categorised horizontally into quarks and leptons. Beginning with the quarks, they are known as the up quark and the down quark, the charm quark and the strange quark, and the top and bottom quarks. The leptons are the electron neutrino and the electron, the muon neutrino and the muon, the tau neutrino and the tau. The bosons, or the force carriers, are the photon, the gluon, the W boson, and the Z boson. Everything we observe in the natural world is constructed from the particles in the first family only, via interactions with the force carriers. The other two families are only found at higher energies in particle accelerator experiments.
It takes two up quarks and a down quark to make a proton, and two down quarks and an up quark to make a neutron. The electromagnetic charges of the quarks add up to account for the overall charge of the proton and neutron. The quarks are bound by the strong force which is mediated by the gluon. The gluon binding energy also accounts for a large amount of the proton's mass, and these mechanisms are described in quantum chromodynamics. Protons and neutrons are bound in the nucleus by the weak force. The weak force is the result of interactions involving the W and Z bosons. The Z boson has no electromagnetic charge, but the W boson can have a charge of plus or minus 1. The electron has an overall charge of minus 1, therefore it binds electromagnetically to the proton. The weak force and the electromagnetic force are described in quantum electrodynamics, which unifies these two forces into an electroweak theory. Interactions in the nucleus also account for the neutrino, which has no charge. All the fermions have rest mass, which is expressed in terms of energy using E is equal to mc squared to convert from one to the other. The W and Z bosons have rest mass, but the photon and gluon have no rest mass. Here we encounter disagreement between theory and observation. Theory predicts that none of the particles have rest mass, and it is therefore hypothesized that in order to gain mass these particles interact with the Higgs field. In quantum field theory, particles are quantizations of fields. The quantization of the Higgs field is therefore the Higgs boson. However, it has not yet been observed. Gluons and photons don't interact with the Higgs field and therefore have no rest mass. Each particle in the Standard Model also has an antiparticle. For instance, the electron's antimatter equivalent is called the positron. There is no difference between the two except they have opposite charges. However, if matter and antimatter collide, they annihilate each other. Shortly after the Big Bang, matter and antimatter would have been created equally. This is observed in experiments. However, everything we know about is made of matter. Recent experiments hint at the fact that there may be an imbalance in the decay rates of matter and antimatter. Antimatter appears to decay slightly faster than matter, and this could account for the fact that we only see matter in the universe, left over from this decay and annihilation process. There is one particle left to mention, and that is the graviton. The graviton is an hypothesized particle which mediates the gravitational force. However, There is as yet no definite quantum theory of gravitation, and the force is still described using Einstein's general theory of relativity. Although the theory is still considered incomplete, it gives a well-detailed account of how atoms are constructed and therefore describes all the elements in the periodic table.